All right. So how about I'm not going to say a more useful application, but this is our formula for calculating the radian measurement of a central angle in a circle, right? We take the arc length, that's S, and we divide it by the radius. But the length of an intercepted arc, right? How we've talked about, an arc length is a piece of the circumference or a piece of the circle. If we took this formula and just multiplied by r, right, here and here in this equation, these r's would cancel. That would give us a different formula. And this is a formula that we could use to find the length of an intercepted arc, okay, where this is an angle and this is the radius of the movement of that angular arm, if you think of it that way. Just something worth noting here is that this theta, okay, this must be in radians to use this formula. All right, so I'm writing this down. Must be in radians. This is the radius, okay, of whatever circle this arc is moving around. We had, and just as a contrast to this, there was a different formula, okay, for finding the length of an intercepted arc that you could use for degrees, but it's a little bit different, right? We use the idea of proportionality to find the length of an arc in degrees. So we would say, if you know what the angle is out of 360, the arc length is the same ratio of the circumference. So this is a formula that gets brought up in geometry class. So this is still an arc length formula if you want, but this arc length formula would be used for degrees. And the formula that we have down here is our formula for radians. Okay, so just to contrast that, both of these can be used. It depends on how the question is phrased, but also keep in mind that if you're given an angle in degrees, you could just convert it into radians in order to use this much simpler formula to get you there. Okay.